This is the video recording for Algebra 2, Unit 5, Lesson 5.9. All right, this is the last new content that we have for Unit 5 here on polynomial functions, and this is talking about how to transform or move those polynomial functions. All right, and hopefully you're going to pick up a lot of patterns of things that we've already talked about here, but let's reinforce it and make sure we really hit it home with this idea of transformations or moving the polynomial functions. All right, so first off here, we got to start with parent functions, understanding what those parent functions generally look like here. All right. And we've got our cubic with our S shape, our quintic with our S shape, our quadratic with our U shape, right? Knowing what these graphs start to look like here. And I know this one's really hard to notice here, but we'd actually have to zoom in on this quintic one and you would see another little bump there, okay? So it is not just it's not just as flat as it looks here. So again, that's where knowing what these shapes are really gonna look like is gonna be helpful for you. So those parent functions, all right? And we talked about this in an earlier unit, right? Those end behaviors, okay? So for 3 and 5, they had opposite end behaviors because remember their exponent is odd, right? And by opposite, we means one side's going up and one side's going down. Versus if we have even exponents, both sides are going to go up or both sides are going to go down. All right. And looking at this one here, the parent function is x to the fourth if we had to choose, right? Because they're both going in the same direction. Now, we had this discussion earlier in an earlier unit here about parent functions and transformations. Okay, so we were able to look at these different transformations, right? Talking about vertical shifting, horizontal shifting, compressions, reflections, all of that stuff. All right, so we were able to talk all about these, and what we did is we came up with a table of basically instructions here. So if we're going to transform the function, right, actually looking at the equation, we would follow this rule. For transforming the table values, right, we would look at the different x and y values and we could calculate those. And then finally what that transformation of the graph looked like, right, actually moving up or down, all of that stuff. All right. Noting here, okay, a couple notes. They wanted to point out horizontal shift versus vertical shift. So x minus k, all right, x minus k, it's inside versus outside, x plus k, all right, and noting that minus is to the right when it's talking about horizontal shifts, but to go in the positive y direction, we have to add on the outside, okay. Now, reflections, again, we had a unit on this already, but reflections of the polynomial function, right? So that's reflecting across that line y equals x. They should look like mirror images across, right? Mirror images across. And we talked about when we reflect across this, we can see if the inverse, right, if the inverse of that function is also going to be a function. So if we look here at our y equals x to the fourth, right, it fails that horizontal line test that we talked about. So the inverse of it is not a function. All right, the inverse of it is not a function. All right, versus this guy here, our x to the fifth, okay, that would pass the horizontal line test, and when it's reflected, right, that inverse is also a function. Okay. Now, when we are reflecting across our x and our y axes, right, what that looks like is plugging in our different values. So the difference here being, okay, if I'm reflecting across my y-axis, all right, if I'm reflecting across my y-axis, I have to have f of negative x. So what that means is I plug in negative x value and then I do my to the power of whatever, right? So for here, it's negative x to the fifth power. So negative 2 to the fifth power is going to give me this negative 32. All right. Versus 1 is going to give me negative 1. All right. But then when I get to my negative values, that negative is going to cancel out. And so I'm going to be left with positive values. So again, just flipping across that y-axis, you have to replace x with negative x. All right, when we flip across our x-axis, right, we take the negative sign out of the x, right? So we make it our negative f of x, all right? So what that looks like here is I still have negative 2 to the fourth power, and then I take the negative value of it. All right, then 2 to the 4th power is 16, and then I take the negative value of that, right? So again, the power of parentheses. Okay, so here is our rules for reflecting. If y equals 5x is transformed to create the x equals 5y, the result is reflection over the line y equals x, right? We replaced y and x, and that was our value there, right? So that's our reflection. Okay, so then again, to translate, moving up or down. All right, we talked a ton about this here, so I want to highlight this as quick as possible. To move upwards, right, we had to add to the outside of that function. So this was y plus 2 because it shifted our values up by 2. All right. If I subtracted it, that would be my horizontal shift down. All right, and then we did talk about the difference between horizontal and vertical. So vertical being my up and down, I'm just going to add it to the outside, versus my horizontal, which is going to be x minus the quantity, right? So inside those parentheses. And again, remembering that if I subtract a value, I'm moving it to the right, and if I add a value, I am moving it to the left. All right, so when a graph is translated vertically, it moves along the y-axis, right? So up and down. So it is the output value that is changed, right? So if we look here, we've got my function plus my k value. So that's going to move it along my vertical axes. That's going to shift it up and down, and that's going to really just change the output value. However, when I move along the x-axis, I'm moving horizontally. And what I'm doing here is my x minus some number, right? So I'm actually changing my input value. I'm actually changing my input value that's going into my expression. All right, so shifting polynomials horizontally, again, reminder, if I've got x cubed by 4 units to the left, so what I'm going to do is I'll add 4 inside the parentheses, and then be able to populate that table, okay, and then graph. All right. Again, the biggest point I want to point out is that every parent graph has one value that's always going to be consistent. So for here, it's going to pass this line 0, 0. All right, so one of the ones that you can start off with is knowing that this is going to be -4, 0 now because you've shifted it 4 to the left. All right, and then again, picking a couple values here to just get the general shape and understanding what an x cubed graph looks like in general. All right. Stretching or compressing, right? So again, to stretch means to pull it away from the x-axis, right? So you pulling it up. And to compress means to push it closer, right? Get shorter and closer to the 0 x-axis. So here, to stretch, you would multiply by a factor larger than 1. To compress, it would be between 1 and 0. All right. So this one is stretched vertically. Okay, we start with our x to the 5th, but then this blue line here, right, it's pulling further away from the x-axis, so this is our vertically stretched. All right, and again, the reason we know that is because it was multiplied by 3, which is a number greater than 1. All right, if we were to multiply by 0.25, what would happen is we would get a compression. We would get a compression of our graph. All right, so what happens when we are reflected across those different functions? Again, how does it look in the function? How does it look in the table? And how does it look in the graph? All right, when it's shifted vertically or horizontally, again, you're going to add or subtract values, and depending on where you're trying to move it, it's going to be either inside the parentheses or outside the parentheses. And then what happens to a polynomial function when it's stretched or compressed? You're going to multiply by some factor, either greater than or less than 1. All right, I'll let you work with those guys. And again, multiple choice questions here. These are going to be what you're seeing on your quiz. All right. Then talking about transformation and behaviors and zeros, relative extreme values. Okay, so a lot of things now we're just adding on here. All right, so noticing here, if we look at this, okay, we can see that we have something to the 3rd power. So we can see that this is a parent function. It looks a little bit more complicated, but we can still see that it's a parent function. All right, and then looking at it here, it's going to have 3 zeros, knowing that this is our parent function. All right, so it's going to have 3 zeros. What's the end behavior going to look like? Well, we would have to look at the exponent, right? So it's x cubed. So one's going to go up and one's going to go down, right? One's going to go up and one's going to go down. Now the question becomes which one goes up and which one goes down, right? And that's going to be dependent on, this coefficient here. So this is -3, and when I cube, right, when I multiply that out, I'm going to get still going to get my -3 value, right? So when I cube these all out, I'm still going to get a -3x cubed. So that's telling me that my left end is going to go up and my right end is going to go down. All right, at most, how many relative max or mins does it have? Well, it can have n minus 1. So it can have 3 minus 1, so we can have at most 2. Is this function a reflection function? Okay, of the parent? If so, what is it? Well, it's got a negative value here. So yeah, it is a reflection. It is a reflection. Now the question is it X, Y, or across that line? Apologies, I skipped over it. But it is a reflection of the parent function over the x-axis, okay? Remember, it's over the x-axis because this is just a negative value of the entire function, not replaced in place of x here, all right? Was the parent function translated to create this function? If so, how? Well, the answer is yes. Yes, because it's got this positive here. Okay, it's got this +2. And it's inside the parentheses with it. So that means we are moving left and right. And since it's a +2, that means I have moved to the left. Oh, left. Okay, so we've moved to the left. Was this function vertically stretched or compressed? The answer is yes, because this is not just a 1, this is a 3 there, right? So it was stretched by a factor of 3. All right, so that's how we're going to put it all together. All right, that's how we're going to put it all together here. All right, we know a ton about this polynomial by looking at this. So we can draw a general shape, right? We can draw a general shape. And now what we can do here is look at comparing some of those polynomials, right? Comparing some of those polynomials. So below here is a graph of a polynomial function and the equation to a different polynomial. All right, so it's saying here, which of these functions crosses the x-axis a number of times greater? Okay, so if we go to looking at the answer here, well, clearly this function, even though it's a higher order function, because I got an x cubed and an x there, so this would be an x to the 5th, right? It clearly only crosses 1 time. And when we look at this guy here, it might not be a little bit obvious, okay, it might not be a little bit obvious, but it reminds us of the parent function x cubed, right? And based on that, we can tell that it's just a parent function that's been a little bit shifted, all right? So if we know our parent function crosses through 0, 0, we can tell that, okay, this got shifted to the left, so this is our new x-axis here, all right? And they might have different values here, but it was actually a trick question. They both only cross the x-axis 1 time. Okay, they both only cross the x-axis 1 time. And now the question's asking is, do either of these functions have an absolute minimum? If so, what is it? So looking at this graph here, does it have an absolute minimum? The answer is no, okay, because this is going to go on and on forever. All right, and if we think about the shape of an x cubed graph, for this one here, it would have the same kind of nature, right? But if we look now here at our x to the 4th and our x to the 3rd, okay, one of these might have an absolute maximum, right? And this would be the -x to the 4th, right? And the reason that is because it's even, which means it's going to have the same end behavior for the left and the right side of the graph, right? And so what we can do here is we can compare maximum values. Okay, so shifting away from looking at that absolute max like peak, we can tell that this function here is going to have a larger maximum y value. Okay, it's going to have larger maximum y value, and the reason that is because the parent function for this one will continue to go on forever and ever and ever into positive and negative infinity. However, this one, like we said on the last slide, is bogged down by the fact that both ends are going to have the same nature. And since this is negative, we're going to have that upside down u, which means it's going to have an absolute maximum y. Right? It's going to have an absolute maximum y. So this one here, if we're not looking for those peak values, if we're just looking to see which one will generate a larger y value, the answer there is going to be our third degree polynomial, right? Our third degree polynomial. All right, and the answer to this would be, okay, the first function will have that maximum value, right? It will have that peak. It will have a maxed y value. All right, this one will not have an absolute maximum value, but it will generate a number that is much, much larger because it will extend infinitely upwards and to the left. All right, so if we plot both of those, this is what they'll look like. So here, this guy here in red is our y to the fourth, right? And this one has an absolute maximum value. All right, this one has an absolute maximum value. This one only has relative maximums. All right, but this one will generate a larger overall y value. Okay, so to compare here, looking at our parent functions, okay, understanding what a parent function will look like, and then understanding that the polynomial functions, now that we know how to read them, will give us a ton of clues as to how these graphs should look. All right, how these graphs should look, and we should be able to match them up, modify them, move them around using a couple key tricks there. All right. Again, going through, checking these, and making sure that you understand, really just solidifying your knowledge of this material.